All right. This is a presentation about how DNSSEC works with DNS and all the basic elements of DNSSEC. So it's not really a tutorial about DNS because I suggest that you should know that already. All right. So we have the DNS hierarchy with the root at the top, and root is managed by ICANN, as you all know. Root has all kinds of delegations to other top-level domains, such as .se and .org or whatever. And .se also has a huge number of delegations for our domain holders. And those delegations are basically NS records with glue for the IP addresses for those domains that are delegated. So this is what it looks like. And then there's a large number of authoritative name services that actually have the name information that you really want to look up from the start. So how it works is that you have some sort of client computer with no internet. And the first thing you have when you start up the computer is that you get an IP address from a DHCP server. So that's the initial trust chain of your ordinary computer at the office or at home. You also get information about a caching resolver, which is how you look up names on the internet. So the first thing that happens after you receive that information and you start using your web browser and want to go to www.is.se is that you ask your caching resolver about what IP address does that name have. And if the caching resolver has just started up, it has basically no information other than the addresses for the root servers. And those are basically hard-coded within the resolver. You get a number of static IP addresses that basically never change for the root servers. So the first thing when the resolver starts up is to actually fill up that hard-coded information with the dynamic information that is contained within the root. So all it knows about is about the root servers. So when you first receive the query about www.is.se, is that query goes actually to the root server from the resolver, because the resolver doesn't know what name service .se or is.se have. So what you get from the root back is that sorry, you don't have a clue about what you're asking about. You should ask .se about that information, because root knows about .se and what name service that have. So what you get in return from root is a referral to .se's name service together with the IP addresses. And the resolver doesn't know where to find is.se still, so it actually goes back and asks .se name service about the same information. And .se also don't know about www.is.se, and in the same manner you get the referral back for the name servers that are authoritative for is.se. So yet another query, but this time you actually get an IP address back, and that's the authoritative information about is.se. So now we have the IP address and we can return an answer to the client. So that's basically how simple it is. And if you want to attack this, there are a number of ways to attack any name server here. You can inject false information. If you insert something from the root replies, you just answer a lot of the queries going from the root. So you can, the problem is that you have a number of parameters that you have to fake. You have the port number and the addresses that you queried and such. All those kinds of information has to match before you can inject false information in the cache. But the simplest way in this scenario is actually put yourself between the resolver and the client computer. And in that way you can actually just respond with any false information. So you want to secure this change because you can basically not trust any of these replies. So we need to add some sort of crypto to this mix. And And what you do is you have asymmetric keys, which means that you have a private component and a public component. So we use asymmetric crypto. And when you have asymmetric crypto, that means that you want to publicize your public keys, so people can make use of them to verify information. And you want to protect the private keys because you use the private keys to generate signatures and encrypt stuff. And in DNSSEC, we have 2 types of keys or key pairs. We have the key signing key that you typically publicize somewhere. And you have the zone signing key that actually signs a lot of the information in your own zone files. So what the key signing key actually do is to make a signature over the whole DNS key set, which means basically the zone signing key that you want to trust when validating the zone file. I will explain all of this in more detail later. And this is what the different types of keys looks like in your zone file. So when you look at the is.se zone file, you discover that you have 2 types of keys, and the only difference between those keys is this information here. It's 1 bit in the information that tells you that it's a KSK or a ZSK. And this bit is actually named SCP, secure entry point. And in general, in general, we don't use that bit for anything in DNSSEC. It's just an indicator what type of operations that you do with the key. And you also have a lot of signatures made by those keys. So here you see signatures over the DNS key record. So as you see, there's a lot of extra information added to your zone just by adding the DNS keys. And the signatures later you can use to validate that the information you have got from a name server is valid in some way. So what is a signature? A signature is an encrypted hash of data. So what you do when you make a signature is that you hash the data with some sort of hashing algorithm, and then you encrypt that data with your secret key or private key. And the hash is just a sort of checksum over the data that you want to protect. And typical checksum algorithms is MD5, SHA-1, and SHA-2, where SHA-256 belongs. MD5 is currently considered very vulnerable. Yeah.
Is it the same true for SHA-1?
It's becoming vulnerable as well. So that's why we want to have a wide option of hashing algorithms available for DNSSEC. So you can easily move over to, or easily, you have to actually change all the name server software, but you can actually move away from an algorithm. So a typical set of DNSSEC signatures actually covers an RR set, and an RR set is a label together with a record type. And if you have more A records for a label, that belongs to the same RR set. So a signatures covers an RR set. So if you have several A records here, you only have 1 signatures covering those. And then we have a quad A record for IPv6 address, and then there's another signatures over that. So there's a lot of extra signatures in your zone files. We also have fingerprints in DNSSEC, and the fingerprints, it's typically just a checksum over key, and not just any data, but typically you call a fingerprint a checksum over key. So why you want that is that a checksum of key is typically much smaller than the actual key itself. So when you want to publish keys in different ways, you want to make that data as small as possible. And the fingerprint is actually made for the DS records. The DS records is published at the parent zone to indicate that the child zone, and the parent zone here is typically .se, and the child zone is is.se. So when you want to indicate that ISE is a DNSSEC domain, is that you publish a fingerprint of the key in .se. So .se has a lot of DS records for all the secure domains. So I'll explain the resolver soon. So instead of the large DNS key blobs that you have in your own zone file, we just publish a short fingerprint of the same key. There's of course different kinds of DS algorithms as well, because there are lots of hashing algorithms. And if you use the domain manager from SC Direct, that registrar creates 2 DS records for every key that we put in the zone. We use both SHA-1 and SHA-256 fingerprints, because we want to move away from SHA-1, but that's still basically required if you want to let all resolvers to trust it, to validate the domains. So what this looks like is that if you have one key for is.se that you want to publish, you get 2 DS records in SE zone if you use the domain manager. Any registrar can of course choose which hash algorithms to use. We basically allows any kind of algorithm to be used. We don't really do validation, I think, of the actual DS data. And if you have more keys, you get even more DS records. And why you want to have more KSK keys, that you might want to change keys after a while. And the way you do that is that you publish the new KSK and move that KSK to the parent zone, and then you can remove the old KSK. NSEC is another concept in DNSSEC. You actually just don't only want to prove that a certain domain exists and is valid. You actually want to prove that domains does not exist as well. And then we have NSEC. NSEC is what .se use today. Another type of algorithm to prove non-existence of something is NSEC 3, which is a little newer. And the way that works is that we have an NSEC for every delegation in your zone. So in .se we have an NSEC record covering every domain with all those records in the zone. So in that way, if someone asks for is06.se, we, instead of just answering NX domain, we add this information to the reply as well, which means that it's a proof that is06 does not exist, because between is.se and is0.se, .se can prove that is06 does not exist because we have an NSEC record. And if you validate the signature with the keys in the SE zone, you can prove that it doesn't exist. There is of course some downside of using NSEC, is that since we always have a pointer to the next domain in next label in the domain, someone can ask for is.se and receive the next label in the domain, which means that anybody can retrieve the whole SE zone or every domain published in the SE zone, which something is good and something is bad. And that's why we also have NSEC 3. NSEC 3 exists for 2 reasons. The first is that you might not want to publish every label in the zone file in the way that so that anybody can just retrieve your zone file and see what's in there. And the other reason is that you might a typically signed zone grows between 3 and 4 times if you sign it using a regular NSEC and DNSSEC. With NSEC 3 you can also opt out signatures, that you only add NSECs for those domains that has a secure delegation using the DS record, which means that you only add a small number of signatures, which of course, just if you don't have any secure delegations, you only get a small number of added signatures. So if you are .com, you don't get suddenly a 4 times larger zone. So that's actually a requirement for a lot of the larger TLDs to use NSEC 3. So NSEC3 is a little bit more complicated. This is a very simple example of usage of NSEC3. It's basically used by UK instead of NSEC, but in UK they have subdomains such as co.uk, which means that they don't have any secret information in the UK zone. So they have NSEC just by that looks exactly like they have NSEC3 looking exactly like NSEC, which means that they don't have any hashing and no iterations with NSEC3. You do hash every label in NSEC3. I'll show you how it looks like. So you can actually use NSEC3 just like NSEC. And there's a number of parameters here. So you have which type of hash algorithm to use when you hash all these labels. You have flags in the next, which means that you use opt-in or opt-out, which means how you generate signatures. And since you don't want to let anybody just build a rainbow table, which means that you can pre-calculate the kind of hashing done in DNSSEC, you can hash something several times, but you also add a salt that you use when you're doing hashing, which means that you have a hash thing that works over a long time, but you can also later roll the salt value. So if someone tries to attack the hashing that is done in NSEC3, that takes a certain amount of time to do it if they want to retrieve all the content of the zone. So to protect it, you can just change the salt if you believe that someone has created a rainbow file to attack the zone. So this is an actual example from .org. Let me see if I can read it. This one has a number of iterations and a salt value. So I won't show the NSEC3 param, but here you can see that the labels are hashed, which means that this has some sort of correct label name, so that if you use the salt value and the iterations value and the algorithm, you can translate this to the correct name later when you validate the content. So this is more convenient. This is regular DNS. This is what it looks like when you don't do any DNSSEC, which is very simple. You can just edit this by hand. So a signed zone file looks like this. This is a little bit simplified, but this is using all the components that we talked about. We have a lot of signatures, and we have a lot of DNS keys. I only have one in this picture. And we have NSEC records. So if you have more data, it grows even more. And you publish the KSK in the parent zone, which is yet another step in the provisioning chain if you want to do DNSSEC. This is something that Anne-Marie is going to talk about, how we at .se handle our KSKs, but typically when you roll or change your KSK, you just have a short time span because you only want to send the key to the parent. But .se doesn't have any root that is signed currently. That will change in July, we hope. So anybody who wants to resolve DNSSEC can just trust root and let TLDs handle themselves. But those who want to trust .se has to configure the KSK in the resolver. And our current policy is that we generate a new key every year for .se. So if you want to trust .se, you have to keep up to date with how we handle our keys. And just yesterday, we generated a new key for .se that we published in the zone. We are going to actually publish that key correctly next Monday, I think. And that's because we are deploying OpenDNSSEC. So we actually waited from January to April this time. But when we publish a new key, new resolver operators must update the key in the resolver to be able to validate the domain. But we also keep the old key for a year, so that any resolver operator that wants to trust .se has a year to change the key or update the key. And if you want to start trusting our keys, you have to find our keys. We have them on our website. It should be HTTPS here, but you can trust either the SSL certificate on the web page, which means that you must trust VeriSign or whoever that is to trust our keys, but you can also verify the content of this blob using PGP. But then, of course, you also must trust PGP, and we have a number of signatures of that key that you might know someone who have put a signature there, so that you can trust somewhere. But then you have to get those keys out of there and put them in your resolver. And in bind, you typically copy and paste it into a bind configuration statement, and you also enable DNSSEC in the resolver, so that you state that I want to validate the answers coming in if I have a trust anchor configured, and the trust anchor is the key from .se in this case. So when we have a resolver configured with DNSSEC for .se, we have a key configured there, and we also told the resolver to validate the information. We can do the same lookup using DNSSEC. So the client here doesn't know anything about DNSSEC. Only the resolver does. So the same query goes for the same address, and the resolver just restarted because we added the key. So we ask the root, and the root in this case is not signed. In a DNSSEC aware resolver, we set a DO bit, which means in the query, which means that this resolver knows how to handle DNSSEC records. It doesn't say anything about if we want to resolve it or not, just that we can handle any kind of DNSSEC records that you send us. But the root doesn't have any DNSSEC things currently. If you do it today, you get signatures back if you do it, but you can't validate the signatures because they are only there because of the long deployment thing that's going on for the root. But we do the same thing for .se, and then we get some additional data back. We got the DS record, and we get the signatures back. And we want to validate those signatures because we have a trust anchor for .se. And what you discover as a resolver is that you don't have any key that matches the signature there, because the signature is made by the zone signing key. And we only have the key signing key configured in the resolver. So we must do an additional query here for the DNS key. And you also, of course, get the signatures over the DNS key back. And then you can start the validation process. First, you validate that the DNS key, the zone signing key, matches what you have in your resolver. And you validate the signature, and when you have validated the signatures, you can find out which key is the zone signing key, which matches the key tag in the signature here. So then you can validate the signatures over the DS. And if all that works, we can continue the queries. And we have the exact same thing here. We get the signature back covering the authoritative answer, the A record for www. And we do the same query for the DNS key, for the zone signing key, but you only do the query for the DNS key because that returns both the KSK and the ZSK. And then you validate the signatures over that. And then you can also validate the signatures over the A record. If this doesn't work, somewhere in the change you get a serve fail back from the resolver, which actually means that something along the line has been misconfigured or that there has been a validation error. There is no real error message specifically made for DNSSEC, which is a little bad, but that's the only indication that you get a serve fail. But if everything works, you get the response back to the client computer with the AD flag set, which just means that the resolver has been doing validation for that query. And that's it for resolving DNSSEC. So if you have any questions on this presentation, you can just put them. Yeah.
How will it work later on when the root is signed? How will it work later on when the root is signed? Will there be a need for implementing the keys in every resolver?
Yeah.
Then too?
How it works is that you only want to have one root key in the resolver, and then you can have a DNSSEC secure change all over if the TLD is signed.
Thanks.